to Rolle's theorem. Rolle's theorem is just one of many existence theorems that guarantee some value c for different things. Rolle's theorem says, let a given function f be continuous on the closed interval from a to b and differentiable on the open interval from a to b. We don't differentiate the endpoints because we don't know what's happening on either side of those endpoints. And let's not forget that when we take a derivative, we have a limit definition of a derivative, and the limit from the left-hand side of the function has to equal the limit from the right-hand side of the function. And if you don't know what's going on to the other side of A, then we have to let that be open. Same thing with the open on the B. Okay, so we have a function that's continuous on a closed interval, differentiable on an open interval. Rolle's theorem says if you know this is true, and also if f of A is equal to f of B, let's take a peek over here. We have a nice continuous function that's everywhere differentiable, so it satisfies the fact that we have a continuous function on the closed interval from A to B. Notice the closed circle, and the function f is differentiable everywhere in between A and B on the open interval. If f of A represents the y-coordinate of the function f at A, so right here f of A is the same as the letter k, is equal to f of B, and f of B is the height of the function, or you could say the y-coordinate at B on the function f, so that's also a k. If these two values are both the same, which means the function has the same height at x equals A and x equals B, this is the same exact height, then what do you suppose has to be true somewhere in the middle? And it has to be dealing with some value of c. We've seen these existence theorems before, and I've had a fit about the fact that we have an interval that goes from A to B, and then they shove the point C somewhere in between A and B, and it's not alphabetical order. But what do you suppose, somewhere in here there's a c value where something is true on this function, and it has something to do with a derivative. And the derivative represents the slope of the tangent line. So what do you see here? Somewhere between A and B and the slope of the tangent line. I'm hoping that you tell me that the slope of the tangent line has got to also be 0 right there. I shouldn't say also be 0 because nothing else was 0 yet. The slope of the tangent line has to be 0 right here for some value c smack dab in the middle. This is a horizontal tangent line, and the slope of the horizontal tangent line is 0. So what does that tell us about f? At some point c, we have to have a horizontal tangent line. How do we write that nice? If f of A is equal to f of B, then there must exist at least one c in the open interval from A to B, such that f prime of c, and f prime of c represents the slope of the tangent line at some point c in between A and B, such that the slope of the tangent line at some point c in between A and B has to equal 0. And it says at least 1. You're guaranteed at least 1. We might have more than 1, but there's got to be at least 1. So again, Rolle's theorem, you have to be given a function that's continuous on a closed interval from A to B, differentiable on the open interval from A to B. If the function evaluated at the two endpoints, f of A is equal to f of B, that tells you that the function is at the same height at both endpoints. If that's the case, then there has to exist at least one c value on the interval from A to B, such that f prime of c is equal to 0, such that there's a horizontal tangent line somewhere between A and B. I want to make a note here, and let's not forget, c an x value. The c value that you find is an x coordinate. It is an x value. It is not a y value. Notice you're applying the c as the input. So the input are your x's. And this, in a nutshell, is what Rolle's theorem is. Given any two heights in a function that are the same, somewhere in the middle, we have to find a point, at least one, maybe more than one. This thing can go up and down 100 times, in between a and b, such that when you take the derivative at c, you get 0 for an answer. Such that the slope of the tangent line at x equals c equals 0. And if the slope of a tangent line is equal to 0, then that tangent line must be horizontal. HTL, horizontal tangent line. HTL, I'm sorry. Alrighty. I'm going to put this in layman's terms a little bit, which are my words for this thing. I wrote this out and I said if, and I'll put it down in words on the board so to make sure everybody understands what's going on. If the height of the function at a is equal to the height of the function at b, that's f of a equals f of b, then there is at least one horizontal tangent line between A and B. At least one, possibly more. And horizontal tangent lines, that's where we're going to find our relative max or our relative min. Sometimes our absolute max or our absolute min, definitely on a closed interval, absolute max, absolute min. Alrighty. Let's do some examples and grind some of this out with some numbers, with some functions. I think I'll leave the picture over there for just a minute. Come over here and let me erase this part of the board. Alrighty. Remember, the theorem doesn't start where it says if. The theorem starts where it talks about f being a continuous function on the closed interval and a differentiable function on the open interval. Okay. Continuing with Rolle's theorem. The directives for the next few questions are going to say, does Rolle's theorem apply? If so, calculate the guaranteed C values. With an S in parentheses because there might be just one, but there might be more. We're guaranteed at least one. So, first example, f of x equals x squared minus 3x plus 2, and we're going to go on -1/4. Does Rolle's theorem apply? First thing, is the function f continuous on the closed interval between -1 and 4? And the answer is yes. F is continuous on -1/4. How do we know that? F is a polynomial function, specifically as a quadratic. Quadratics are continuous on all real numbers, the whole domain, and we don't have any denominators messing us up. There's no variables in the denominators that give us that restriction on our continuity, and there's no root symbols to play around with any even roots, have any undefined values. So this function f of x is defined and continuous on all real numbers, so of course it's going to fit with an interval from -1 to 4. Second question, is f differentiable on the open interval between -1 and 4? And certainly it is. Polynomial functions are nice smooth functions. They're everywhere continuous and everywhere differentiable. Nice friendly functions. So f is differentiable on -1, 4. Last thing I need to know is f of -1 the same thing as f of 4? Because I need those two heights to match up in order to have in order to get that c value that's guaranteed by Rolle's theorem. So let's find f of -1. It's -1 squared minus 3 times -1 plus 2. This gives me 1 plus 4 plus 2. 1 plus 3 plus 2. That was good. And that answer should be a 6. F of -1 is equal to 6. Now let's find f of what? 4. So we're going to take 4 and square it, minus 3 times 4, and then plus 2. Again, just put your input of 4 into the original function. 4 squared is 16, minus 12, plus 2. So 4 plus 2 is again 6. And what have you found? You found f of 4. And right back here, I guess I should be saying, therefore, -1 is 6, therefore 4 is 6. So you can see I have 2 points with the same exact height. So all of this information together, the fact that f is continuous on the closed interval, oops, differentiable on the open interval, let's make sure to get that right, and the fact that f of -1 is actually equal to f of 4, and they both have a value of 6, okay? F of -1, I should write that someplace. F of -1 is equal to f of 4. Because these three things match up, everything's nice, then I do know that yes, Rolle's theorem does apply. So now I have to calculate the c value, calculate that guaranteed c value. The guaranteed c value is where f prime of c is supposed to equal 0. So therefore I need to take my function f of x. F of x is equal to x squared minus 3x plus 2. And I need to take this derivative, 2x minus 3, and find what value for x. Remember I told you before that the c value is an x value. I don't need to change this to c. I just need to recognize this c when I'm finished. I need to find out what c value is going to make this equal to 0. So I put a 0 in there and set the derivative equal to 0. This gives me 2x is equal to 3, x is equal to 3 over 2. You can call that 1.5, 1.5. So that's my c value. C value is 3 over 2. I'll leave it as 3 over 2 because I like fractions. Alrighty. So, what does this look like? I'm going to go ahead, I'm going to see if I can squeeze my little graph right in this area. How's this? What does this look like? Take a look right down here. How's that sound? So I have a nice xy axis. I have a point that is what? -1, 6. So -1, 1, 2, 3, 4, 5, 6. I have 4. 1, 2, 3, 4, 5, 6. And this is definitely a quadratic. It's nice and smooth. I can tell that my y-intercept, if I put a 0 into the original function, I'll get a 2 out of that. So 0, 2 is going to be a point on my graph. My axis of symmetry is going to be right in between a -1 and a +4. One number is smack dab in the middle between a -1 and a +4. If you ever want to know that, you take the average of -1 and 4, which means you add them up and divide by 2. -1 plus 4 is 3, divided by 2 is 3 over 2. Surprise, check that out. So my axis of symmetry is going to be right along x equals 3 over 2. This is not a asymptote, even though it's a dotted line, it's just my axis of symmetry. So now I'd like to take 3 over 2 and put it back into my original function so I can at least see what the y-coordinate would be. I'm just going to go here. F of 3 over 2 is 3 over 2 quantity squared minus 3 times 3 over 2 plus 2 on the end. Shorten that up a little bit in that space. F of 3 over 2, square 3 over 2, you get 9 over 4. Multiply by 3 over 2, this is minus 9 over 2. And then plus 2. I need a common denominator to add my fractions. This will stay 9 over 4. This one will become 18 over 4. You multiply top and bottom by 2 to get a common denominator. And then 8/4 is the same thing as the number 2. 9, take away 18, add 8 to it. What's that going to give us? Should be a -1. Common denominator was a 4. We keep it. This is f of 3/2. So therefore, we have just found an xy point. 3/2, comma, -1/4, and that is my vertex of the parabola. So I come over here, 3/2, -1/4. I might be drawing that just a little bit too much. My parabola should be nice and smooth, coming up like this, coming around, coming back, and up like this. I'm not really sure about these x-intercepts. They look like they might be a 1 and a 2. I'm not quite sure. I'm just going to let it go. We have our parabola. We have A here at -1. We have B here at 4. These two have the same exact height. See that? That means that somewhere between -1 and 4, we're guaranteed a horizontal tangent line. Do we see it? Of course we see it, right here at the vertex. There's our horizontal tangent line, right like this. This tangent line has a slope of 0. And we are guaranteed that f prime, the slope of the tangent line at 3/2, is indeed 0, and it looks it. So this kind of wraps everything all up. Something I want to point out is that the difference between these two graphs, there's plenty of differences between the two graphs, but for this one in particular, I'm looking at my A being a -1 and my B being a 4, and it turned out that slope of the tangent line turned into a 0 right smack dab perfectly in between -1 and 4. Now we're guaranteed a C value in between -1 and 4, but not exactly in between -1 and 4. So the reason it works that way in this case is that this is a parabola, and our horizontal tangent line occurs at the vertex. And we do have a line of symmetry and everything's nice and sweet. But that C value doesn't always have to be exactly in the middle of your interval. Come over to this picture, which I drew earlier. I had my interval from A to B. Look at that C value. It doesn't look like it's smack dab in the middle whatsoever. All right. Plus, we could have more than one C value. I could have a function that goes up and down a few times, and I can pick this point and this point. They're the same height. And look, we have horizontal tangent line here, horizontal tangent line here, horizontal tangent line here. So it's possible to have more than one horizontal tangent line in between your interval from A to B. As long as A and B are the same height, you're guaranteed some horizontal tangent line. Maybe 1, maybe 2, maybe 3, but at least 1. I'll give you a second to take a peek at that. Forget that. You can hit pause if you want, can't you? Okay. So I'm going to erase this stuff from left to right, and I'll leave the directions up on the top, and I'm going to set up another problem for you. Did I say I was going to erase from left to right? That was kind of silly, because it looks like I'm going from right to left. Alrighty. Example 2. Same kind of directions. Here my function is going to be f of x equals, and I'm going to give you x plus 3 over x minus 4, and we're going to talk about the closed interval from 0 to 8. Does Rolle's theorem apply to this function on that given interval? Well, what must be true? First thing that has to be true is the function has to be what? The function has to be continuous on that closed interval. So is f continuous on 0, 8? And that, I'm hoping you're saying to yourself, there's no way. Looks like we have a what here? Your denominator equals 0 and x equals 4, but the numerator doesn't. So we have a vertical asymptote. We have I'll write out vertical asymptote. When x equals 4. And 4 does look like it's smack dab in the middle of our interval there. And it really wouldn't matter if this said 7, or if this said 2, or if this said 10, or if this said -8. As long as 4 falls in there someplace, the function will not be able to have Rolle's theorem apply to it, because the function is supposed to be continuous. We have a vertical asymptote at x equals 4. This function is not continuous, so therefore, no. Rolle's theorem will not apply. And if Rolle's theorem does not apply, do I have to go ahead and calculate the c-value guaranteed by it? I would hope you'd say no. We're done. As I said, if so, calculate the guaranteed c-values. So we're finished with this example. It's nice when the function itself isn't even continuous and we can stop after the first test. This, by the way, was example 2. Let's move on. See if I can fit example 3 real quick. Here my function f of x is going to equal the absolute value of 2x minus 6 minus 4, and my interval is going to be 1, 5. So, is this function f of x, which is the absolute value of 2x minus 6, quantity minus 4, on the closed interval 1, 5, is this function using Rolle's theorem? Can it use Rolle's theorem? Does Rolle's theorem apply? Well, is f continuous on 1, 5? This is an absolute value function. We should know what absolute value functions look like. They're in the shape of a V, they have a vertex, and they have the domain of all real numbers. So therefore, yeah, f indeed is continuous on 1, 5. Next bullet. Is f differentiable? On the open interval between 1 and 5. That's my thought process, that's my question. Well, I know that something's going to mess this absolute value thing up, because I'm going to have some kind of a vertex, which is a cusp. And we know we have to pay close attention to cusps anytime. Functions are not differentiable at cusps, we know that. The question is, will the cusp fall within this interval, or is it outside of the interval? So we need to take a peek. A lot of people are going to think this minus 6 means that I'm going to move to the right 6, which therefore I would be outside of my interval and I'd be good to go. This 2 is going to mess you up slightly. So I'd like to take a peek at that. F of x equals the absolute value of 2x minus 6 minus 4. There's a few ways we can talk about this, but you remember that minus 6 right there, the thing that's being added or subtracted to your x, can only be added or subtracted to your x in order for you to view your horizontal shifts left and right. I need to get that 2 off there. So I need to factor the 2 off. What goes in parentheses here? X minus 3. Now I can see that this is actually a shift to the right by 3, and this, of course, is a shift where? Down by 4. This 2 right here is what we call a vertical stretch. So, I'll just take it kind of simple here. Y equals the absolute value of x. Looks like this. And we're going to use our thought process on transformations in order to get this thing done. We need to shift to the right 3. 1, 2, 3. Down 4. 1, 2, 3, 4. So 3, -4 is where this vertex just moved. It moved to the right 3 and then down 4. And now I need a vertical stretch of 2. So instead of having a nice slope of 1 and a nice slope of -1, I now need to have a stretch of 2, which is going to make my slope go twice as steep as what it normally would be. So I've got to go up 2, right 1, up 2, right 1, up 2, left 1, up 2, left 1, and this becomes my absolute value function. Now, that thought process could have been in your mind like boom, 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 and you'd have this thing graphed. At the very least, you can pick some numbers, plug them in, and make sure you're getting the values that come out of here. This is 4, -2. This is 5, 0. Over here we have what? 2, -2. Over here we have, and this should be, if you ever miss it, just make it a little bit darker. Okay, a little bigger. This is 1, 0, 0, 2. So you can read these points right off your graph. Now I'm on the interval from 1 to 5. So I'm just looking at 1 to 5, from here to here. Is this function differentiable everywhere between 1 and 5? And the answer is no. We have a cusp. All right, the slope coming towards x equals 3 from the right-hand side is a +2. The slope coming towards x equals 3 from the left-hand side is a -2. This derivative from the right does not equal the derivative from the left, and therefore the derivative at 3 does not exist. So no, f is not differentiable on 1 to 5, and it's because of that cusp at 3, -4. Therefore, Rolle's theorem does not apply. Okay, so you can box this whole thing if you'd like. Okay, you can box this whole thing if you'd like. But Rolle's theorem will not apply in either one of these cases. The first one, we don't even have continuity. The second one, we have continuity but not differentiability. I'm going to erase the board again. We're moving on to example 4. Somebody erase the board from right to left. See, set it like that time. Let's see. What does example 4 want us to show? F of x is going to be given as x squared plus 5x minus 2. And we will be on the interval from 2 to 6. Yes. Does Rolle's theorem apply to this function? F of x equals x squared plus 5x minus 2 on the closed interval from 2 to 6. Well, first question. Is f continuous on this interval between 2 and 6? Well, f of x is a polynomial function, specifically a quadratic. It's everywhere continuous. So yes, f is continuous all over the place, but definitely on 2, 6. Second question, is f differentiable on the open interval from 2 to 6? Well, f of x is a polynomial function. Polynomial functions are everywhere continuous and everywhere differentiable. So yes, f is differentiable on the open interval between 2 and 6. Next thing I need to test. I need to find to see whether or not this function is at the same height on both endpoints. So I need to find f of 2. F of 2. Let's see, 2 squared plus 5 times 2 minus 2. This gives me 4 plus 10 minus 2. 14 minus 2 is 12. So I have f of 2 is 12. This gives me the point 2, 12. Remember, every time we do a substitution into the original function, we find a y-coordinate, and we like to pair it up when we're finished by saying, therefore, my input-output combination is this xy coordinate point. I've lost my room down here, so I'm going to come over here and I'm going to say, what is f of 6 now? So let's do 6 squared plus 5 minus 2. I think you can already tell this is not even going to come close to happening. So 36 and 30 gives you 66. Take away 2 is 64. I have found f of 6. Therefore, I have the point 6, comma, 64. And what do we notice? We notice that f of 2 is not the same as f of 6. This is the doozy right here, and we have Rolle's theorem does not apply. So we don't have to find the C value guaranteed by the theorem if the theorem is not applicable to the problem. Example 5. F of x equals, let me find 5. X cubed plus 2x squared minus 5x plus 3. And let's go with the interval from negative 3 to 2. Let's see. I'm going to analyze my function a little bit. I know this is another nice polynomial function. Polynomial functions are everywhere continuous and everywhere differentiable, so the first 2 bullets are going to be good to go. F is continuous on negative 3, 2. F is differentiable on the open interval between negative 3 and 2. My third question is going to be, is this function at the same height for both my endpoints? So I need to test f of negative 3. I really don't feel like doing that. So I'm going to come over here with my negative 3, and I'm going to hit synthetic division using my coefficients. I have a positive 1, a positive 2, negative 5, and a positive 3. I'm not missing any of my exponents. Everything's filled in, so I don't need any 0 placeholders. Bring down my 1. This gives me a negative 3. Combine, I get negative 1. Negative 3 times negative 1 is 3. Combine, I get negative 2. Negative 3 times negative 2 is 6. Combine, I get 9. 9 is my remainder. And if you recall the remainder theorem, it says you can evaluate a function at a given answer, not answer, but input, and the y value, the output, is the remainder that you get when you do synthetic division like that. Then you can trust me on that, or you can go right ahead and you can plug that negative 3 up in there and do all that work. I now have to also test f of what? 2? 2 is not so bad. I think I'll actually plug the 2 in. I can do whatever I want. Just show that it's the same thing. 2 cubed is going to give me 8. This is also 2 cubed, so I get another 8. 5 times 2 is 10, minus 10, and then plus 3. So I have 8 and 8, 16. 3 more makes 19. Take away 10 gives me, you guessed it, 9. So I have f of 2 is 9. Once again, see, I forgot that. That should be negative 3, comma 9 down here. Therefore, I have 2, comma 9. So what do you notice about these 2 points? They have the same height. The same height. So what will that give me? I think I'll erase my synthetic division here. You guys can always rewind and see it again if you want. I'm going to have a little space. This information right here, we have continuity on the closed interval, we have differentiability on the open interval, and we have the fact that f of negative 3 is indeed equal to f of 2 because they both equal 9. So all this information tells us that yes, Rolle's theorem applies. And if it does apply, I need to now calculate the guaranteed C value. So I need to take my function, f of x equals x cubed plus 2x squared minus 5x plus 3. Now what C value are they talking about? They're talking about that C value that says f prime of C has to equal 0. So I need to take my first derivative, set it equal to 0, and solve for my input. Here's my first derivative. We're using power rule. This is just 3x squared plus 4x minus 5. I need to set the first derivative equal to 0. This will give me the locations of any horizontal tangent lines. And it looks like here I'm taking a peek and trying to see if there's factors. I'd really like to factor this and use the zero product property to get to my roots. But it doesn't look like I'm going to do that. I can't think of a couple of numbers here that multiply to get my 15, negative 15, and combine to make 4. So I think I'm going to go for the quadratic formula. Quadratic formula says x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. My b is 4, so my negative b is negative 4 plus or minus the square root. I always square my b and put it in first, so 4 squared is 16 minus 4. I always multiply my ac together. 3 times negative 5 is negative 15. All divided by 2 times a, which is 3. Coming up here, x equals negative 4 plus or minus the square root of 16 minus the negative product will give me a positive, and 4 times 15 is 60 all over 6. X equals negative 4 plus or minus the square root of 76 over 6. These are my c values. However, I will break them up, and I will say, can we call it c now? C is negative 4 plus the square root of 76 over 6, which is approximately, I'll get to that in a minute. And the other c value, oh, we're going to have 2 c values this time. We're going to have to take a peek at this and see what it ends up looking like with a graph. I end up with negative 4 minus the square root of 76 all over 6. I take my handy dandy calculator someplace, which is over here. And I can pop that into my calculator, get those decimal equivalents. I like using the alpha y equals and grabbing my numerator denominator idea. Negative 4 plus the square root of 76 all over 6. I'm looking. Just don't remember that being my answer. Is that my answer? And if I went the other way, these look like these are my c values. And I think that does it for now. I'm going to go back on that because I don't think I saw that answer before. Anybody see an error anywhere? Double check something with my handy dandy gadget. We're good. I think we are good. Those previous things that I have on that paper must come from a different example. All right. So we have some cubic function that's going up and down and up and down. It has a positive leading coefficient. So it's a cubic function with a positive leading coefficient. We're starting low and ending pi. We're going from -3 to a +2. We have -3, 9. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we are going all the way to what? 2, 9. So 1, 2, 9 is right up here. Other than doing that, I don't want to graph it. Let's take a peek at what the graph looks like on our graphing calculator. Looks like it's going up to, let me see here, -3, -3, 9. It looks like it goes beyond here, comes up. Let's hit my max on my calculator so we can do this fast, a little faster anyway. Take a peek at what this looks like. We got -2.199. This tells me that this is the location of a max, which will make sense to me. Way up here at 13 something. It's going to go way up there. Let me look one more thing for myself here. Let me back on my trace menu. So this is going up. It's coming down. It looks like it wants to touch the x-axis, but I don't think it does. And it comes back up, and like I said, if you miss your point, just kind of make it a little bigger. There you go. So what we're finding here is a horizontal tangent line right here, where my C value is -2.119. C is approximately -2.119. And we have another C value. We have a horizontal tangent line right here, horizontal tangent line again. And this C value looks like it's smaller. It's about, C is approximately 0.7862. And I'm accurate to at least 3 decimal places. I'll put the 4th one on there. It really doesn't matter. As long as mathematically we are accurate to 3 decimal places or exact. So this is what's happening with our cubic function. We end up with a max and a min. But these are our C values guaranteed by Rolle's theorem. And that, in your 5 examples, I think wrap things up just a little bit. Let's just make sure we understand Rolle's theorem. Rolle's theorem says, first off, you have to have a function that is continuous on a closed interval. You have to have that same function be differentiable on the same open interval. Evaluate the function at both endpoints and make sure you get the same height. If you have the same height, you're guaranteed to get some value in between those two x values of your beginning and your end of your interval, such that you have a horizontal tangent line, or f prime of C equals 0.